Hello, everyone. My name is Jonathan. I'm an engineer at Grafana Labs. And today we're going to be talking about Mimir 3. And in particular, we're going to be talking about some new features that are coming later this year with Mimir 3. As usual, if you have any questions, you can add them to the Slido, and we will answer them at the end. So the major themes of Mimir 3 kind of orient around a few things: reliability, performance, and cost. We're going to hear quite a bit about how Mimir 3 improves cost throughout this talk. At Grafana Labs, we operate some of the largest Mimir clusters in the world, and we also work with customers, and I've spoken to some of you here who also operate very large Mimir clusters. And we've taken what we've learned from those operations experiences and incorporated them into Mimir 3, which is coming later this year. So we're excited to talk about some big new features that are going to be part of Mimir 3, and the two features in particular that we're going to be talking about today are ingest storage and the Mimir query engine. But before we talk about the new features, I want to set the stage by talking about Mimir 2 so we can understand how it works as a baseline. So this is a high-level diagram of the Mimir 2 architecture. The way the Mimir 2 works is request processing comes in two different paths. So on one path, write requests come into distributors, and distributors are responsible for taking a write request, inspecting the samples and values inside of it, and breaking those apart and forwarding them onto ingesters. Ingesters are responsible for indexing the data that comes into Mimir and making it available for querying later on. Read requests come in through a separate path and eventually make their way to queryers. And queryers will query recent data from ingesters and then aggregate the results and send it back to clients. The main thing to note about this architecture is ingesters are central to everything. So ingesters sit in between both writes and reads. So we think of this architecture as having a write path and a read path, and ingesters play a role on both of those paths. This works out most of the time. This is fine, but occasionally ingesters can become overloaded. This happens, for example, if we get a large burst of queries or if we get some very expensive queries that come in. Those queries can put a lot of load on ingesters. And the load from the read path from queryers can end up impacting ingesters' ability to serve the write path. And so this is one of the challenges with the current architecture. Taking a look at how the write path works a little bit more closely today in Mimir 2, each sample from a write request gets replicated 3 ways for reliability. When we look at each series and each sample that we receive, we shard the series ID. So this is a way of figuring out what we want to do with the series, and that helps determine which ingesters we're going to forward the series onto to store it on. We attempt to replicate each sample to 3 ingesters, and once we've heard from 2 of those ingesters, so 2 out of 3, that the sample was stored successfully, then we consider the request to be successful and we respond to the client. The way the read path works is a little bit similar in that queryers are looking up series on some ingesters. So if a querier is interested in some series, it shards the series IDs to figure out which ingesters the data lives on, and it'll query the data on up to 3 ingesters and look for a response from 2 out of 3 ingesters. Once it receives a successful response from 2 out of 3, so again a majority, then we consider the query to be complete and have all the data, and the querier will respond to the client. By using a majority on both the write path and the read path, we're able to make sure that our data is stored across multiple nodes in case there's a failure, but we're also able to make sure that we have a complete set of data on the read path. Things get a little bit more interesting when we spread data across multiple zones. So Mimir has this ability to spread ingesters across multiple availability zones to provide better availability. So in this diagram, we can see we have zones A, B, and C. And if we lose one zone, having additional zones or having your ingester spread across additional zones allows you to keep serving data, write requests and read requests. But in this diagram, you can see we have an ingester that's unhealthy in zone A and an ingester that's unhealthy in zone B. And when using multi-zone replication, availability becomes based on what is going on with the majority of zones. And in this case, since the majority of zones is unhealthy, our read path would actually be unhealthy. This is more likely to happen in larger clusters, but it's something to be aware of with the current Mimir 2 architecture. So now that we've seen a bit about how Mimir 2 works, let's talk about Mimir 3, and we're going to start by talking about ingest storage. So as I mentioned before, ingest storage is a new architecture option which we're introducing in Mimir 3, and the goals of ingest storage is to provide better scalability and resilience than we saw with Mimir 2. Ingest storage starts with Kafka. So Kafka is central to the read and write paths in ingest storage. The way it works is distributors, as before, still write data. So write requests come into distributors. But rather than forwarding write data to ingesters, distributors are writing to Kafka. Ingesters, as we saw before, were kind of a central component, but they move over and become a read path only component. So ingesters consume data from Kafka in this architecture. Queryers query from ingesters, as they did before. But the main thing to note about this architecture is Kafka allows us to divide and decouple the read paths and the write paths, which provides better resiliency than we've had with Mimir 2. In Mimir 2, ingesters have an additional responsibility of building large blocks and periodically uploading them to object storage. In Mimir 3, with the ingest storage architecture, we're able to move that responsibility to a separate component. And being able to have these types of responsibilities in individual components allows us to better scale those components based on their unique loads, which is another benefit of this architecture. Of course, this architecture does mean that we have Kafka. But it's not actually Kafka that we depend on, it's the Kafka API. At Grafana Labs, we've talked about how we use WarpStream in place of Kafka. So we've written about our usage of WarpStream on our engineering blog. WarpStream is a Kafka API-compatible cloud service that's backed by object storage. So we use this in place of Kafka, and it's worked really well for us. But the key thing to note about this Kafka dependency is, like I said, it's a dependency on the Kafka API. So you can use Kafka, you can use WarpStream, you can use Redpanda, you can use some other Kafka API-compatible cloud service. Whatever works for you, you can use it in Mimir with ingest storage. As we saw before, one of the downsides of the current architecture is when the read path becomes unhealthy, the write path could be impacted. But this slide kind of just illustrates how when the read path becomes unhealthy, like when ingesters become overloaded, which can happen occasionally in large clusters, the write path is still healthy. And so this is a huge benefit of the current architecture by using Kafka. So I want to look at what the new architecture looks like a bit more closely. We're going to look at the write path and the read path in particular. So starting with the write path, distributors are still responsible for distributing series as before, but rather than distributing samples to ingesters, they're writing to Kafka partitions. So Kafka partitions are a way that Kafka uses to divide data so that it can better scale its data processing and storage internally. And they also allow us to better scale our read path, as we'll see in a little bit. Each sample that comes in gets sharded by its series ID to figure out which partition to write to. And we only need to write to one partition one time. So this is a little bit different than how things worked with Mimir 2, where we wrote to a majority of ingesters. Kafka takes care of making sure that the data is highly available later on the read path. One trade-off with this approach is we are waiting for a response from Kafka from a distributor. So there can be increased latency on the write path using this new architecture, depending on which Kafka implementation you're using. Like I mentioned before, at Grafana Labs in our cloud, we use WarpStream. WarpStream is backed by object storage, so depending on which Kafka implementation you're using, you might have an additional latency cost going round trip to something like object storage. Let's look at how the read path works. So the read path is interesting. The way it works is one ingester consumes from one partition. So each ingester consumes from one and only one partition, a Kafka partition, that is. But you can have multiple partitions or multiple ingesters consuming from the same partition for high availability. So that way, if one ingester goes down, you can still have another ingester that's available and able to serve queries for some partition. The neat thing about Kafka and partitions is that the ingesters consuming from a partition have a complete set of the data. So with Mimir 2, we saw how a query needs to access some series on a majority of ingesters or in a majority of zones. But with ingest storage, you can get a majority, or you can get a complete set of the data by querying just a single ingester in each partition. So the quorum size, in other words, is 1. By having a second ingester, though, we can add high availability. So in order to have all the data, we only need one ingester per partition, and for high availability, we only need two ingesters. And this availability approach, by using partitions, is actually much stronger, as we'll see in a moment. To better illustrate what the availability looks like, earlier we saw how with multi-zone replication in Mimir 2, if you have ingesters unavailable in a majority of zones, then your read path would be unhealthy. But with ingest storage, you can actually have ingesters that are unavailable in each zone. You can have ingesters that are unavailable in each partition. As long as you have one ingester available in each partition, your read path is still healthy. So this approach to replication and availability is much more resilient, and the probability of a read path outage is much lower. And you can decrease the probability of a read path outage by creating more partitions. And you can control how many partitions you create. You can create dozens or hundreds. And this chart kind of shows what the probability of an outage looks like. So this chart is comparing the probability of a read path outage in Mimir 2, which is the blue line, compared to Mimir 3 with ingest storage. As some number of ingesters start to fail along the bottom x-axis, you can see the probability of a Mimir 2 outage can increase quite quickly. But with Mimir 3, with ingest storage, we can lose lots of ingesters, and the probability of a read path outage stays quite low. So this is due to the fact that we're consuming from partitions, and ingesters have a more complete set of the data than they had before. So this is a huge benefit of the new architecture. But something else that's interesting about this is it's actually not an apples-to-apples comparison, because this chart shows the probability of an outage using Mimir 2 with 3 zones worth of ingesters. But in Mimir 3, this data, the data that feeds this chart is only running 2 zones worth of ingesters. So we're running a third fewer ingesters, and we have massively better availability. This is a huge benefit of the new architecture and something we're really happy about. As you can imagine, running fewer ingesters also translates into lower costs. So this is a chart that shows the resource usage of a Mimir 2 cluster that we migrated to Mimir 3 with ingest storage. And this is one of our larger clusters, and as you can see, the total resource usage, so this takes into account CPU and object storage costs, decreased by 15%. This takes into account the additional cost for us to run and use Kafka, or using WarpStream in our case. But even factoring in that cost, we're able to run fewer ingesters, which more than offsets the cost. And we expect that when using ingest storage, you'll either be resource and cost neutral or see a cost decrease. So to recap, ingest storage is a new architecture option coming in Mimir 3. It helps provide better efficiency and resource usage than you had in Mimir 2. And next, I'm going to hand it over to David, who's going to talk about some other Mimir 3 features.
Okay, how's it going, everybody? I'm David. I'm going to be talking about the Mimir query engine, which is a new foundational feature in Mimir 3.0. It provides a lot of new improvements to analysis power, reliability, and cost. Who cares about cost? Anybody? Okay, shout out to cost. All right. First, I'm going to talk about the analysis power. So Jonathan said we run some very large Mimir clusters. This is true. We are frequently asking pointed questions about these clusters, the huge numbers of pods, the huge numbers of disks, and so on. I know you all are interested in your huge numbers of volcanoes and cars and stuff like that. Here is a question I asked last week. What's the average CPU usage in the entire cluster? So this kind of query has a simple result, but it can potentially touch tons of data. And what happens sometimes when we have like 10 million containers? Unfortunately, you can run into an error like this. Anyone seen this error before? The chunks error, the chunks limit. Okay, good. So if you're trying to do analysis, this is a roadblock for me. I have to figure out how to constrain my query to get it to work, or like issue 3 smaller queries and like scotch tape them together afterwards. It's a bummer. As engineers, we would rather see this query coming across and say, you know what? Yeah, that's an expensive query. I can tell. but we're going to execute it anyway without destroying the system, and we're going to give a result back to the people. So I'm going to switch gears a little bit and talk about the same problem, but from a different angle, and that is running a Mimir cluster. No one in here runs a Mimir cluster. I already asked a few, and I'm pretty sure no one runs one. Am I right? Okay, I guess I'm right about that. We run a bunch of Mimir clusters. Here is one of them, and this is a Mimir 2 cluster. So this is actually a pool of query pods, and the squiggly lines you see, it's memory usage. As you can see, the memory usage is just kind of all over the place. So we have to tell Kubernetes how much memory we want, and that's how much we pay for. So the bummer about this is most of the time we're not using anywhere near that much memory, so we're kind of just leaving cash on the table. And the other thing that's a bit sketchy about this is if we go over the yellow line, we can be killed by Kubernetes. We will issue errors to our customers. We'll get paged. We try to stay out of the danger zone. So we have a couple knobs for staying out of this danger zone. One of them is this dynamic you see, which is we're paying a bunch of cash to be overscaled. We're wasting a bunch of money. And the other one is, well, you've already seen that too. It's the error. So we put these limits in the system to protect the system, to keep from crashing, to keep from running out of memory. So if we could flatten these spikes out significantly, we would stand to spend a lot less money because we could take that yellow line and move it way down. And you folks issuing the queries could do analysis that touches a lot more data. So that is the motivation for the Mimir query engine. And I'm going to tell you a little bit about how it works. So Mimir is built on top of Prometheus. It largely strings together Prometheus components to build a more scalable Prometheus. And one of the things it does before Mimir 3 is use the Prometheus query engine to execute queries. So the problem is when your queries load massive amounts of data, the Prometheus query engine uses massive amounts of memory. And I'm going to show you why the Mimir query engine tends to be a game changer for these gigantic queries. So here's how it works, and here's how the Prometheus query engine that we used in Mimir 2 would execute this example query, sum over disk used bytes. So the question is, how many disk used bytes are we using in the entire cluster? So the first thing it does, it says, okay, sum of disk used bytes. First thing I'm going to do is go out and grab the disk used bytes. I'm going to go out to storage, fetch them, load them all up into memory, and it could be a massive amount of data. It could be, 5 gigs or whatever. This is the source of the memory spikes that we saw in the previous slide. And once it's all loaded into memory, it sends it on over to the sum operator and computes the sum. Easy. So I'm going to show you how the Mimir query engine would execute the same query. And the big difference is we work on streams of series this time. So the first thing we do, sum of disk used bytes, go out and just get the first series, send it on over to the sum operator and start a running tally. Go ahead and get the second series, stream it over, and so on until you get the final result, which is the same that Prometheus computed. So this massively reduces peak memory usage because we're only looking at a small window of data at any given time. And we have a benchmark that covers this exact query, and the results are pretty staggering. We use 92% less memory, and we are 38% faster at executing the same query. So I'm showing Thanos in here too. They also improve upon Prometheus. They are a little bit faster than us in the latency department. That's because they parallelize more. We're not doing that yet. I think we might. Okay, cool. I like this chart even more. So as we ratchet up the number of series that we're pulling in, you can see Prometheus and Thanos go linear with memory. And we're all in almost a different algorithmic class here. We're using constant memory. That's really cool. So we knew we were onto something good with this query engine. So we didn't just implement summations. We have implemented 100% of stable PromQL grammar. So that means not only does that summation toy query work, but all these hairy operational queries that exist in your runbooks and that glue your system together, they also get to take advantage of streaming. So that's streaming. That's not the only feature of the Mimir query engine, by the way. I'm going to talk about this other type of query that we see quite often at Grafana Labs. This is a success rate query. See it a lot in web apps. What's the percentage of succeeding requests? So the interesting thing about this query is the success term appears multiple times. Yeah, actually, some of our clusters, 20% of the time is spent executing a query that has the term in there twice. And let's add the data plane into the mix and see how the Prometheus query engine would execute this query. Success over success plus failure. What do I do first? I'm going to go out and grab success. Okay, next up, success. What am I going to do? I'm going to go out again and grab it from the data plane. And failure, I'm going to grab that too. Okay, it has loaded success multiple times. It's the same data, it's not changing. So the Mimir query engine knows what's going on here and identifies that is a duplicate term in the query, and it goes and fetches it one time instead. So it's a third less load operations against the data plane, which reduces load on your ingesters and store gateways. Okay, so this optimization is good. I mean, for you compiler geeks or whatever, this is the common sub-expression elimination. It's a common optimization. We don't just implement this one. We actually implement an entire framework where we can keep on adding these kind of transformations and optimizations over time safely. So if we return to our resource hog query that I showed you before, we'll be more likely to get a result like this instead of the scary error that we saw before. Okay, so as we've enabled the Mimir query engine at Grafana Labs, I have some results to show you about that. And the caveat is, if you know anything about Mimir, the performance of Mimir is highly dependent on the kind of queries you're serving. So this is one favorable result. Your results could be much better or a little more mediocre or whatever. But see if you can discern when we turned on the Mimir query engine. Okay, so it's 3x less memory. We can take that yellow line from before and ratchet it way down and just save a lot of memory, save a lot of money right away. And so will you this year when it comes out. And how about CPU? It's a similar story, 80% less peak CPU. CPUs are expensive. You'll be able to save money there too. So when Mimir 3.0 drops this year, the Mimir query engine will be the query engine. So you'll get it just by upgrading, and it'll be in the open source Mimir. Okay, so we've talked about ingest storage. We've talked about the Mimir query engine. Both of them conspire to bring you better reliability, performance, and lower cost. So we're excited about getting these and other enhancements to Mimir 3 in your hands later this year. Come see us at Ask the Experts. Some of you have. Others should too. Well, thanks a lot for the attention.